Okay, so now let's talk about how utilities actually try to predict demand far out into the future in order to make decisions about how much capacity to build. Um, Before we do that, let's take a step back and actually ask a more general question, which is how does anyone try to predict anything in the future? And the answer is that first we have to be able to explain the past, and utilities do the exact same thing when they're trying to make projections of future peak demand. So let's say we have 16 years of observed data, so historical data of peak demand in megawatts. So the highest demand value in any given hour for each one of these individual calendar years, as well as an associated economic index. It's unitless, also kind of made up here. This isn't real data, but let's say we have some measure of economic conditions in our given area, where a higher value of the number indicates higher economic activity, and a lower value indicates lower economic activity. Population of people in our service area in millions, and then again some sort of unitless metric that measures per capita consumption of electricity. So sort of efficiency. In this case, we're saying the higher the value, the less efficient, and the lower the value, the more efficient, so the lower the per capita energy consumption. So we could use that historical data to build a simple predictive model. In other words, some way mathematically to estimate what peak electricity demand is going to be in some sort of future year, given forecasted or expected values in these series of other explanatory variables, right? So economic activity or population or per capita electricity consumption. And so what we have here is an equation where yt on one side of the equation is the predicted peak electricity demand in some sort of future year t. And we're saying that that's equal to three different terms here. AWT plus BXT plus CZT. And so A, B, and C here are just coefficients. They don't, they're weights, in other words, right? So the higher the value of A, we're saying the stronger a predictor WT is in terms of determining a value of YT. So we have these three coefficients, A, B, and C, and then these other terms, WT, XT, and ZT, where WT is our economic index in year T, XT is the population in millions in year T, and ZT is the per capita consumption of electricity in year T. So essentially what we're trying to do here is find the values of A, B, and C that give us the best fit between YT, our estimate of peak electricity demand, and actual observed peak electricity demand. And so we want to find the values of A, B, and C that do the best job of predicting the value of YT using that historical data that we just looked at. So in other words, we want to be able to have values of predicted peak demand that if we plotted them on the y-axis and plotted corresponding values of actual peak demand in all those years on the x-axis, we would get some sort of almost linear relationship that's not perfect, but is pretty good. In other words, it closely follows a one-for-one line. So if we find out what these values are of A, B, and C, and there's lots of different ways of finding what those values are. One would be least squares regression. Let's say we find the specific values of A, B, and C that no matter what value of W, X, and Z we put in for the same year, it gives us a pretty good estimate of what the value of YT would be. And let's say we come up with these optimal values of A, B, and C, then what could we do next with this model that we just built? Well, we could substitute in new forecasted values of WT, XT, and ZT that might represent future expected population, future economic productivity, and future per capita energy consumption. And by substituting those values in, we would get future values for peak estimated demand. So, are we missing anything in our simple model of predicting electricity demand? So here's a hint. This figure shows average temperatures from January to June over the entire contiguous United States from 1900 all the way up to 2010 or 2012. And the blue dots, the blue signal, is actual recorded temperatures. The green line is sort of a smoothed or filtered signal, and then the red is just a linear trend. So the linear trend shows the gradual increase over many, many years, over decades and decades, in temperatures over the contiguous United States. So this figure actually shows two different things that we might need to worry about. The first is climate. Climate we were going to refer to here in a very simple way as the slow-moving change in average conditions over time. So it would be that red line, that linear trend. Weather is actually the noise that bounces around the average trend. So we could think about climate as being the slow-moving change in red, and blue being this year-to-year variability, where on average it's increasing over time, but on a year-to-year basis it bounces around a lot. Some years it's really high, some years it's really low. So when we're thinking about predicting future electricity demand, which do you think matters more, climate change or weather? Well, it kind of depends on time scale, right? If we went out 100 years into the future, maybe climate change would matter a little bit more than sort of the noise around that climate signal. But if we're just trying to think about what electricity demand might be in 5 or 10 years, actually the bouncing around the trend gives you way bigger jumps and dips, peaks and valleys, than the slow moving red signal. So I would say that in the short term, at least on the order of years to decades, really uncertainty in weather is a bigger thing to incorporate in predicting future demand than climate. So, knowing what we know about electricity demand and how it increases with cooling demands, and we're Duke Energy, let's say. So, we're in the Southeast, and peak electricity demand occurs in the summertime, probably during the hottest part of the hottest day of the year. One other variable that we might want to add to our model is some measure of maximum average daily temperature, the average temperature on the hottest day of the year. And so we can also keep track of that here and see how it might impact our estimates of peak electricity demand when we add it into the model as an explanatory variable. So what would that look like? We would add one more term to our predictive model here. We have one more coefficient, a d, and then we also have a new term to describe some measure of weather, for example, temperature on the hottest day of the year. So let's say we redid our regression analysis or our approach for finding the best values of A, B, C, and D, and we have this new model that is better able to predict peak electricity demand or explain peak electricity demand in the past based on a combination of the economic index, population, per capita energy consumption, and what the daily average temperature was on the hottest day of the year. So if we want to take that model that works in terms of explaining the past and now apply it to the future, how would we pick a value of VT, in other words, that hottest day of the year, to use in our prediction of what peak electricity demand is going to be like next year or the year after or 10 years from now? So one option would be to treat VT as what we call a random variable. So it's a variable that can have a lot of different values, but some of those values are more likely than others. And we can describe that relationship using a probability distribution or a bell curve here. So we could use the normal distribution to describe the different values that VT could take, as well as the probability that VT takes any given value. And so here on the y-axis, we'd have the probability, and on the x-axis, we'd have the maximum annual temperature. And the values here on the x-axis are just standard deviation. And so all this is showing is that you have about a 38% chance of being within half of a standard deviation away from the mean or the average hottest temperature over the historical record, and that it becomes less and less likely to get values that are either really high or big departures above the expected value or the average temperature on this hottest day of the year. And it also gets less likely that you get temperatures on that hottest day of the year that are very cool. So we could play lots of games here. We could take 100 random samples of corresponding values of VT and plug them into our equation, assuming we had forecasted values of WT and XT and ZT. And what we would get are 100 corresponding values of YT, or predicted peak demand. And then it would be up to us as the utility to figure out what level of risk we're willing to accept. In other words, when I talk about risk, now we might end up with a probability distribution after our little Monte Carlo simulation, where we have probability on the y-axis and on the x-axis peak system demand. This is one way of measuring how likely different levels of peak demand are going to be out into the future based on our forecasts, as well as our uncertainty analysis about the weather. So we might come up with some sort of average expected value for peak system demand out into the future. And that doesn't mean that that value is going to occur. It just means that it's the most likely single value to occur. And that if you move above that expected value or average, or you move below that value, those values become less and less likely to occur. And so for utilities, they're in the business of making sure that they have enough generation capacity. And so certainly they don't want to err on the side of under predicting what demand is going to be. But the question is, what level of risk are they willing to accept? So another way of thinking about this is to say, well, looking at this bell curve, and the percentage and the area under the curve, what we can see is that there's a 50% chance that peak system demand out into the future for this given year is going to be greater than the average, right? And so that means that if we decide to just build the amount of capacity into our system that would satisfy average demand in a year, then 50% of the time we're not going to have enough. We could also say, we want to build enough capacity so that 95% of the time we'll have enough capacity. Or we could say, we want to build enough capacity so that 99% of the time we'll have enough capacity, or 99.9% of the time we'd have enough capacity. So ultimately, it's up to the utilities and also regulatory bodies that are overseeing their decision making to figure out how much capacity they should build based on some sort of measure of probabilistic risk.